Hi everyone, I am Subhabanik. I am a Masters of Engineering program student at Concordia University. In this presentation, I will show how to design a two-stage OPAMP using Cadence by step-by-step process. I hope you all enjoy this video. Let's begin. First of all, I would like to design this circuit. This is self-bias two-stage OPAMP. I will design this circuit using 45 nanometer bulk CMOS process. First of all, let's consider some specifications. Let's say I use VDD 1.2 volt as well as my ICMR range is 0.4 volt to 900 millivolt. Moreover, I took phase margin greater than equal to 60 degree, and as well as there are other some conditions. Now I will show you how to design the first block, mean the first stage differential amplifier. After that, I will design the second stage. My first step is, from phase margin, I should determine this compensation capacitor CC. That is the relationship between CC and our load capacitance. And using this formula, I found my CC should be greater than equal 800 femtofarad. Here, for design purpose, I used CC 1 picofarad. My second step is to determine the tail current of my OPAMP. Tail current means the current which will go through this two branch. This current has been determined by this M5 transistor. However, this is also related to our slew rate of an OPAMP. So let's begin and try to design this M5 transistor. Here is a common relationship between our tail current, slew rate with our compensation capacitor. From here, I found our tail current should be 20 microampere. Here I assume slew rate 20 volt per microsecond. To design purpose, I select ID5 to 25 microampere, a little bit higher from the calculated value. Now, I should design the aspect ratio of my M1 and M2 transistors. You know, this M1 and M2 transistors is nothing but my input stage. This M1 and M2 transistors are related to the gain bandwidth of my two-stage OTA. This is the formula to determine the GM1 and 2, means the transconductance of my input stage. Here I found my transconductance is 315 microsiemens. Using this GM1 value, there is a common formula, or you can say a relationship between ID, mu, and CUX, WYL with GM. From here, I can calculate our aspect ratio for our M1 and M2. However, how can we determine the mu and CUX value? You should know this mu and CUX is related to our technology parameter. But we can determine its value using DC analysis. But for this, if I want to find the M1, if I want to calculate the mu and Cux value for NMOS, then I should configure this NMOS with a direct connected load. And then I should provide my necessary bias current. You know, just now I calculate or I assume my biasing current is 25 microampere, and my each of branch, if these two voltages are equal, then this current is split into these two branch. If it is 25 micro, then each of branch will flow 12.5 microampere current. So each branch is responsible for carry 12.5 microampere current. Therefore, in this case, I selected 12.5 microampere. In this case, I should select the maximum W and L ratio. For a good design, it will be better to take this W by L aspect ratio 1. For 45 nanometer bulk CMOS process, the maximum width and length is 10 microampere. Therefore, I choose 10 micro. It's the same case for PMOS. We have to ensure this MOSFET should be in saturation. Therefore, there is a diode connection configuration. If I show you in Cadence window, then you also can find this circuitry. These are the two circuits where I find the mu and CUX as well as the mu p CUX value. Whenever you will DC analysis and you can see this beta effective point. From this beta effective, beta effective mean is nothing but mu and CUX W by L. We know here W by L ratio is 1. From this, we can find the mu and CUX value. In my next video, I will show how can I do decisional simulation in Cadence. Just for now, I want to move forward. Similarly, from the same case, here I found mu PCX value is 262 microsiemens. And for NMOS, it was 363 microsiemens. From there, I found my W by L1 aspect ratio is 10.93. Now I would like to design my top PMOS, this two PMOS. This two PMOS is a current meter configuration. However, I can find this W by L ratio for MP3 and M4 using this formula. But here I also have some difficulty. However, this transistor is related to my ICMR plus value, which I estimated 0.9 volt. Here, my challenge is to determine VT3 max, mean the maximum threshold voltage for this M3 or M4, as well as I have to find VT1 minimum. So now let's see how can I design or how can I find this VT1 as well as this VT3. To find VT3 max, I should configure this circuit. And as I told you, my each of branch is responsible for 12.5 microampere. Therefore, I connected 12.5 microampere with the drain of this PMOS, as well as other circuitry are same. Here I intended to use L equals to 200 nanometer. Therefore, I choose here L equals to 200 nanometer. However, the threshold voltage of PMOS does not vary too much with width. Therefore, I can take an arbitrary width. There, in this case, I took 2 microampere as a width, and I found BT3 is 418 millivolt. However, for design and simulation, and it is easy, and as well as there are some other factors. Therefore, I took a little bit higher value from this BT through this calculated value. You also can find this circuitry in the Cadence. This is the circuit from where I can calculate the VT of this PMOS. Now we have to determine the VT1, mean and max. And I'm telling you, VT1 mean is related to ICMR minus. On the other hand, ICMR plus is related to VT max. And to find this value, I have to configure this circuitry because this two circuitry and this current source is representing the PMOS transistor. And my intention is to determine the VT of this NMOS. And you can, if you assume this is our PMOS, which are carrying 12.5 microampere, as well as this is my tail current, which is supplying 25 microampere. And in this case, first of all, I should apply ICMR minus, means 0.4 volt, and then I should do DC analysis. From DC analysis, I can find the threshold voltage. And here I found it is 463 millivolt. Whereas whenever I applied 0.9 volt in this circuitry, I found VT1 max 523 millivolt. Similarly here, I took a little bit higher value that I found after DC analysis simulation. Moreover, one crucial point is this: what about W by L ratio? For W by L, we already calculated the W by L aspect ratio, which was 10.93. And as I told you, my intention is to length equals to 200 nanometer. From there, I can easily determine the width of this transistor. You also can find the circuitry here. From this simulation, I found VT1 mean and VT max. It is very important to configure this circuit. Otherwise, my calculation might be wrong and my circuit might not work properly. Therefore, it's very crucial to determine mu and CUX, mu P CUX, as well as the maximum and minimum threshold voltage for NMOS as well as PMOS using appropriate circuitry as well as appropriate bias current. Now I can move forward, and I found using this formula that you already seen that my W by L 3 by 4, this ratio is 0.84. So now my M1, M2, M3, and M4 are complete. Now I have to design the M5 transistor, which is my tail current, which is supplying my tail current. And to design M5, I'm telling you, this M5 is related to ICMR minus, and this is the associated formula. And using this formula, I found there is a negative value. This negative value indicates that my ICMR minus might not 0.4. Definitely not. This value should be increased, or either this VT1 max value should be reduced, because my Vita 1 and twice ID1, these are already fixed. My ID1 is 12.5 microampere, as well as my mu and CUX and my WYL ratio also fixed. So I can play with this VT1 max. Otherwise, I can increase the ICMR minus value. But it's really very hard to play with the threshold voltage of MOSFET. However, I believe that uh, I can use ICMR minus greater than equals to 750 millivolt. In this case, my all of the circuitry might be in saturation mode. If you remember, I'm talking about this M5 transistor, and this VT1 is nothing but my input stage. And if you just look this circuitry, this has look like this. And this this VD set is nothing but the drain current of my M5. Moreover, this VD set also represents the source voltage of my M5. Therefore, it is very crucial to determine a voltage in Vin such that my M1, M5 should be in saturation mode. Now let's see what is the condition to make this two transistor in saturation. If you assume this is my M1 and this is my M5, and there might be some other circuitry, then what is the V in mean? Which is I'm telling ICMR minus. To keep saturation M1 and M5, I have to provide the overdrive voltage of MOSFET M1 as well as overdrive voltage of my M5 plus the maximum threshold voltage. So from this simulation, you can find easily the VOV. VOV is nothing but is VGS minus threshold voltage, VGH minus VTH. VGS minus VTH is also called the overdrive voltage. When you will do the DC simulation, you can find this voltage, as well as from the same for M5. You also can see the threshold voltage for M1 and M5. And you should take the maximum threshold voltage. Let's say if M1 threshold voltage is 0.5 and M5 threshold voltage is 0.6, then you should take 0.6. And I found this V in mean should be 778 millivolt. For design purpose, I use ICMR minus 780 millivolt. That is the minimum condition to keep both transistors in saturation mode. However, using the formula, I also can calculate WL5. And the formula is, we know the ID5, and this is the condition, or this is the formula in MOSFET ID in saturation mode. And we also calculate VD set. Here, I use the same VD set, 0.21. And I found WYL in 3.12. I wrote here 5.8 because the WYL ratio of this M5 transistor as well as the WYL ratio of this M8 transistor should be same, because you can see this is a simple current meter like this. For your kind information, this M4 and M6 is also in current mode configuration. Now, my first stage is done. My next work is to design the second stage, which is nothing but the M6 and M7 transistor. To design M6 transistor, which is my PMOS, as well as my input for the second stage, the GM6 should be 10 times higher from the input stage GM to maintain my phase margin greater than equal to 60 degree. And as I told you, this uh, this PMOS are in a current meter configuration. Therefore, these formulas are also true. W by L6, W by L4 equals to ID6 divided by ID4, as well as it also related to the GM ratio. If this formula are true, then we can move forward. So we can find the GM4 because I know ID4 mu PCUX I've already calculated. We also determine W by L4 ratio. So using this, I can calculate GM4. After finding GM4, we can calculate W by L6 ratio. And you can see this is my second stage, my PMOS, and there is one NMOS. And there are a same current flow through my PMOS as well as NMOS. So ID6 should be equal ID7. So let's try to find ID6. As I told you, this PMOS and this PMOS in current meter configuration, if you see, then this formula is also true. And from there, we can calculate the ID6. Once we have found this ID6, then we can calculate the W by L7 because this is also a current meter configuration. Mean this NMOS and this self-bias NMOS also in the current meter configuration. And middle of this, if you have remember, there was my tail current source. And after all of the calculation, I found all of the W by L ratio. I calculate the width and the same length for all of the transistors to be a good design as well as for layout purpose. It's also easy to the layout as well as to matching all of the circuitry. However, this value is not guaranteed that you will find your desired output. To find your desired output, you might be play with this circuit, especially play with the W by L ratio, not L. My L is fixed, the W all of the transistors. Now let's try and I want to show you my circuitry. Once you have done all of the stages and when you have found you all of the things appropriately, then these are my circuitry. If I start from the input stage, then you can see my total width is 4.5 micro. And from my calculation, you might find it 2.2 micro. I just increase this width because, gain is related to my GM. If I can increase my GM, my gain will some increase. And GM is also related to width. If I can increase the width, then my GM will increase. In the long run, my gain will increase a bit. But you have to determine that, or you have to check every time if all of this MOSFET should be in saturation mode. These two transistors are same as my calculated value. This width was, as far as I remember, 170 nano. I just slightly reduce this way because uh, from the small signal model, if I tell you about this circuit, you can find that the gain of this circuitry is nothing but the GM, then the output resistance of this top PMOS parallel the output resistance of this NMOS. In small signal model, this point will be grounded. It's mean if I can increase the resistance, then I can also increase the gain. If you think about a common source stage, the gain is GMRD. If you can a little bit increase in RD, the gain should be increased. You also know the resistance is inversely proportional to V. Therefore, I slightly reduce the V. As in the long run, my resistance a little bit increase. But for the same, I have to check my all of the transistors should be in saturation. The rest of the circuitry are same. Here, I will also increase a little bit width of this transistor. Now, if I do the disassemblation, then you can find every parameter. I don't want to vary any parameter. Just save this operating point, and I have to check my input voltage. This input voltage I am providing 680 millivolt. And I have to check my all of the transistors are saturation in or not. For my negative terminal, I also have to provide the same 680 millivolt. My VDD is 1.2 volt. Now let's check all of the MOSFET are saturation or not. We can find DC operating point of these. Here I can find my this value is in region 1. This means I have to increase this value a bit because as I told you in this input terminal I should provide 200 voltage plus 1 threshold voltage. Let's try 750 millivolt and check again. It is still now in region 1. Sometimes ago I simulated the circuit, then everything was okay. But right now, what is the problem? Okay, I am removing this, and it will easy for me to provide voltage over there. Oh, I forget to increase this voltage. I have to enable all of the voltage source. Now we can see this MOSFET in region 2. I firmly believe all of the transistors should be in region 2. This is obviously region 2. These two are direct connected. You can see. Check this one. Okay, my all of the transistors are in region 2. Then we can do SC analysis, and as our target was to find gain greater than or approximately equal to 40 dB, let's try to check it. For this, I'm providing an AC signal in my positive input. However, biasing is always important. I'm using acid magnitude is 1 as amplitude, let's say 20 millivolt, and frequency I'm using, let's say 10 kel. What is the problem? Okay, I forgot to activate this. Here you can find my AC voltage. Whenever this is my magnitude is 1, on the other hand, it is providing 85 volt. Okay, let's try to check the gain of this circuit. For gain, I should select output divided by input. And this 4 pico is my load capacitor. And this CC is 1 pico, which is my compensation capacitor. And we can find its gain is approximately 38 dB. We also can find the 3 dB gain from this curve. 3 dB gain is not this 3 dB. 3 dB gain is my low frequency gain minus 3. It's mean 35 dB. I can say my 3 dB gain is 35 dB. At that time, the frequency was 290 kilohertz, and its unity gain frequency. Unity gain frequency mean how it is gain is 1, mean near 0 dB. I can find near 0 dB point near 20 megahertz. At that point, I should look at my phase. Then I have to find the difference between this value from 180. So I can find 76 degree. 180 minus this value is, I think, 76 degree. So my target was to get phase margin greater than 60 degree. I achieved my both of this condition. Now let's see and try to check the unity gain performance of this circuitry. To check the unity gain circuit performance, I should connect my negative input to the output terminal. Now if I do a transient analysis, I can find my input and output. Sorry, I have to save this circuit. This was unity gain response. In my next video, I will use this OPAMP and try to check some performance parameter such as is slew rate, is CMRR ratio, is power consumption, and so on. If everything is good and satisfactory, I will use this OPAMP, and I will also make some interesting circuits using this OPAMP, such as I can use this OPAMP in band gap reference circuit. I will also use this OPAMP in capacitive DSC circuit. However, that's for today. I hope you will enjoy my video, and if you have any confusion and any question, please make a comment. I surely try to answer your every question. And I believe the formula I have shared, you also find this formula in popular analog electronics book. And if you use this formula and the method I have shown you to find mu n cox, mu p cox value as well as the threshold voltage value, using this formula, you can easily implement this two-stage OPAMP. Bye for today. Take care. If you love my video and if you think it is interesting, please share my video with your friends as well as subscribe my channel